Good afternoon, everyone. This week we continue with the uninformed search. Uninformed search, we already finished breadth first search and breadth first search and depth first search last week. So it will also be required for your project. So you need to select one to implement. And we also have analysis on these two algorithms. So we already found there's some problem with the depth first search, DFS. So that means it is possible, that means maybe not optimal. So that will be an issue for us, correct? So next one, we want to talk about how can we implement a better algorithm to make it optimal. So this is the first thing we want to talk about today. Okay. So we develop an algorithm called IDS, iterative deepening search. Iterative deepening, that means we want to do the search deeper and deeper. But each time we set a limit, and then within this limit we use the DFS. If we cannot find the goal, and then we can deepen the search, deepen the depth of the search. So for example, if first one is depth equal to 1, second one is depth equal to 2, and so on and so forth. So till we find the answer. So this one we avoid the problem with the DFS. For example, DFS, it will go further as long as it can go further. So that means maybe you waste your time till you exhaust your time. You don't have time to find the answer because the time is due. Okay. So this is just to revise that DFS or modify it to make it optimal. Optimal, of course, with the condition, that means the cost for each step is not very small, or there's not uncountable steps within one layer. If it's uncountable, that means you cannot exhaust all the nodes in one layer. That will be not possible. So that's called an iterative deepening search. Okay, use DFS as a subroutine. So that's why we put the DFS here. So that means that within each round we still use DFS, but each round we increase the depth of the search. Okay. So first one, check the root. That means this is like the depth equal to 0. If the root is already the goal, then you can stop. So that means we already found the goal. We can return. Okay. Otherwise, we need to set the depth to 1. Correct? Okay. Do a DFS search for a path of length 1. Path of length, that means that's the total, the maximum path, the maximum cost allowed for your search. So that means this means we set the path equal to 1, set the depth equal to 1. That means at most you can search within the next layer. Okay, so that each time we just expand the next layer nodes, the nodes in the next layer. Okay, and then if there's no path of length 1, do a DFS searching for path of 2, path of length 2, so on and so forth. Okay? Only after we cannot find the goal in the current layer, we will continue with the next layer. But within the current limit, for example, within this range, for this part of the search tree, we use DFS. So you can find this is similar like a combination of BFS and DFS, both BFS and DFS. So we use DFS as the major procedure, but we are using BFS to guide the search stage. So we search layer by layer. Of course, we don't just read layer by layer. So even here, so if you deepen the depth, you still need to search based on DFS. So you still need to start from the root till if you can find a node in the depth 1, continue and depth 2, and then you cannot go further. So because now the the length of the depth is already 2, so you have to return, and then so on and so forth. So that means within this is part of the search tree, partial search tree, you are still use DFS. So DFS is the major procedure. But we incorporated the idea of layer by layer from the BFS to perform the search or the rounds of the search. So this is the idea. That's why we call it iterative, right? So we do an iteration along the depths of the search tree. Each time we expand only one layer beyond, and then within that small tree, whether we can find the answer based on DFS. If we can find DFS solution, we can stop. Otherwise, we can increase the depth by one more. Okay. So let's look at an example like this one. So for example, we first search the root. Okay, starting from here, search the root. If we use this one, that means we visit that node. Okay, and then if we cannot find it, we search within this tree. This tree will have only 2 layers, root layer and the layer 1. So root layer you can just think about as layer 0. Okay, within this limit equal to 1, you first visit this one and then use DFS. First go with this 1 and then continue. If you cannot continue, you need to visit this one and then go back. Okay, just so go back and then visit the next one. So on and so forth. So this one, of course, is similar like with post order. Okay? We first go deeper, and then when we return, we said that we visit that node. So you can find here, we first go to root. So that means it's first is B, right? And then we have C, and then A. So in fact, we start from A, right? That's called a post order. Of course, you can also use write in different way. You can use when we visit, we just list the node visited A and then B, C. That's also is the same. Okay, it's the same. So the only difference is that pre-order or post-order. I think you may learn this one in your structure course, okay? Data structure. Okay. Anyway, this is just the ordering issue. If we cannot find the goal, we need to deepen the depth by one more. So that's the limit equal to 2. And then we continue use the DFS. So A and then B and D. If we can go deeper, we go deeper. Okay? So if we cannot go deeper, we visit it and then return to the upper layer and then go deeper to see whether there's siblings, any siblings under that node. If we have, we go deeper and deeper. If we cannot go deeper, we visit it and then return, visit this one, finish this branch. And then visit there's any other sibling under this root node. Yes, we have one, and then go deeper and deeper. We cannot go deeper, we visit it, and then to see whether there's other siblings, visit it, because there's no other children to allowed to go further. So visit this one and then visit this one and then return visit this one. Okay. Continue. Limit equal to 3. Go further and further, go further and further, and then visit it and then return and then further and then visit it and then next sibling and then return, continue, cut further and further and so on and so forth. Okay, till we find the solution. So this is the iterative deep learning search algorithm. So if I ask you to write a pseudocode, you can just use the DFS as a function and then call DFS, and then within the outside you have a loop. Okay, you have a loop. Okay, or you can have the loop. You can use a while loop or use repeat until. Okay, so this one, if we don't know the depths, so we may use repeat until there's no nodes to expand. Okay, do well or just like that. Okay, I believe in our book maybe we have pseudocode. Maybe you can just check it. Okay. Let's look at the properties. Similar like the previous one, we know BFS, DFS. We know BFS is optimal and complete, but the DFS is not complete, not optimal. Okay, let's look at. So whether it's complete, if there's no, for example, no the extreme case, there's many nodes in one layer, we can say it's complete, okay? So it's yes. And then optimal, similarly, this one, because we expand layer by layer, if we reach the goal, reach the answer, so that will be must be the smallest cost, okay? The path must be the smallest, because we have examined all the even smaller one we haven't found, then we expand, so of course that one will be the smallest. Okay, if step cost is equal to 1, so we add this condition. The reason is that we want to avoid the problem as well. We mentioned if it's there's many nodes, each node is very small, and then there's an uncountable one, so we cannot reach the optimal answer, because you cannot exhaust all the nodes in some layer. Okay, so if each step cost is 1, so that means okay, maybe this is yeah, it's better we explain to this one to complete. And then this one, the main reason is that here optimal means if we find the answer, the answer is the best. So this one is based on layer by layer. So the path cost, in fact, is just like the depth cut. How many, for example, if you visit in the layer 1, you find this optimal solution. So the cost will be from the root to this layer 1. But this has an assumption. Each step cost is the same, cut is the same. So step cost, that means you go from one layer to the next layer, they're the same. But if, for example, some layers are they don't follow this way. This cost, this is 1, this is 2, but this is 1, this is 1, and then this is 1. Maybe this one is even better. For example, this is 4. Cut. So you find the nodes in the 0, 1, 2, 3, but your cost is 1 plus 1. 1 plus 1 plus 4, okay? Layer 1, layer 2, layer 3. So layer 1, layer 2, layer 3. But this one, the cost is even the layer is more than this one, but just because of each layer, the cost is different. This is 1, this is 1, this is 1, this is 1, okay? So it's 1 plus 1 plus 1 plus 1. So in total is 4. This one in total is 6. So even you find the L3 you got the answer, but maybe there's another one which the cost is even smaller. Okay? So the cost is layer 4, which is only 4 for this one. So this is really depends on the question. Okay? If your question can define like this one, each cost is the same. For example, like you play games and so on, like the search the maze. So moving the tile from one room to another room, the cost is the same. So definitely you can use this method. There's no problem using IDS, DFS, BFS. But if for some other problem, maybe you need to consider. For example, like we mentioned about like the Traverse Man problem. So you want to visit all the cities within using the small amount of time or the small amount of distance, smallest distance. So you find a path to visit all the cities in a map. Okay, you can repeat or not repeat. There's 2 types. If like that, that will be different, because that one, the map, each 2 nodes, their distance are not the same. So 2 cities, okay, from Long Beach to Gulfport, and then from Gulfport to Long Beach to New Orleans, right? They are different, right? Gulfport to Long Beach is maybe only 2 miles, for example. Okay, but for here, maybe it's 75 miles, correct? So that's different. So this one is a different problem. So when we do the DFS or BFS, we cannot use this one, because this one we cannot guarantee get the answer will be the optimal, correct? So later we talk about if based on this one, if the step codes are not the uniform one, that means uniform means they are the same. If step codes is not uniform, non-uniform, so which other algorithm we can use, we'll explain later. Okay. So here just need to know, okay, it is yes for complete and yes for optimal. Only the condition is that the step cost is uniform. And then time. Okay. So for time here is you can find how to do analysis on the time. You just think about the expansion procedure. So for example, you expand layer by layer, and then the lower level layers will be expanded more times, because each time you need to expand it, right? For example, like previous example, like this one, right? You can find. So when we expand it from here, we expanded the layer 1, and then layer limited equal to 2, we expand layer 1 again, right? And limited equal to 3, we expand layer 1 again. So how many times for us to expand the layer 1? It depends on the depth, right? So that means we can say it's 3 times. And how about the layer 2? Is 2 times, right? 1, this is 0, and then 1, 2, right? 2 times. And how about the layer 3? Is only 1 time, right? So that means this one can be considered based on the depth of the optimal solution. For example, if the depth of the optimal solution is 3, so we know this one is expanded 1 time, right? So the depth of our optimal solution we know is D, right? We use D to represent the optimal solution's depth, the cost or the path cost, and then use M to represent the maximum, okay? Maximum search depth. So for this one, you know how many nodes on this one. So that means because each one, for example, is starting from 1, and then the branching vector maximum is B, and then this is B square at most, okay? And then this is B cubic. So that means we know this is so we only expand this layer is only B square, okay, 1 time. And then this is just because the depth is D equal to 3. That means D minus 2, okay, is 3. And next one, you need to have more expansion. So you know the depth number of nodes is this is B square, okay? And then the next one is dB. So this is dB. So how many search? Then you need to expand how many times? This is for layer 1, and then this is layer 2, layer 3, okay? So if we search till the depth D, we find the answer, and then we will expand layer 1 D times, and then at most there are B nodes in this layer, because we now found the upper bound, okay? We do time complexity, we want to get the worst case, what will be the value it cannot exceed, okay? That's the maximum, okay? So at most you will expand this layer 1 dB nodes. So that means B nodes is for layer 1. So you can find in this layer 1 is number of nodes is less, okay? So you can find this one we expand only 1 time. It has most number of nodes, more number of nodes. That's why you can find well, maybe this one is time consuming, but in fact, because most of the nodes are on the lower layers, and then on the shallow layers, higher level layers, their number of nodes are not many. It's only b times, okay? It's only b, and then b squared. That means that we do exponential is growing. So that's why in fact the time is still comparable to the DFS. Okay, this is the general solution is this one: d plus 1, b0, b, and then d minus 1, and then till the last one, b to the power of d. Okay, so this is the d plus 1, b0 is just a root node. Okay, this is one time, and then you reach d level, you must expand the root node d plus 1 time, and then layer 1, layer 2. So we have that one we already mentioned, layer 1. So each layer, so that means you can have the layer I, and then you have a layer I. This is I plus 1. Okay, it's like this formula. Okay, like this one. If I equal to 0, then that's d plus 1. If I equal to 1, that's db. If I equal to 2, layer 2, that's L minus 1, d minus 1. Sorry, d minus 1. So that means that you can just conclude a description for this one, and then you can just use sigma, right? I from 0 to d, right? In total is d. 0 is the root. Okay, so that means, and then d minus I plus 1, and b to the power of I times. That will be time, because this is just that means the time is depending on how many nodes you will grow. Of course, the spatial complexity is the same, right? Will also be the same, because you need to save these nodes. Okay, the same. Sorry, this is still like the previous issue. You don't need to keep you don't need to repeat the nodes. So at most, it's BD, right? It's on that level. Okay, on that level. Let's look at this one. So this one, in fact, is big O to the power of B to the big O of B to the power of D. So this is the same equation that we mentioned before. Okay, it's series, and then you can use that one to do the summation, because basically d plus 1 or d minus 1 doesn't matter. You can just delete this one, d minus something. So you have the b0, b1, b2, and then b to the power of d, and d is a constant according to this b something, so you can get rid of d as well. So you only have like a b 1 plus b and plus b to the d. So that one will be 1 b to the power of d plus 1, and then 1 minus b, correct? So this one will be a constant. So till finally you get b to the power of d plus 1, and the b to d plus 1, so you can have another one, correct? So it's b multiplied by b to the power of d. So that constant also can be ignored. So finally you only have b to the power of d. Okay, and then the space is just how many nodes we need to save in the memory during the search. So because this is like just you want to maintain data structure for this one. For example, like this one, we can use a queue, and then we save the nodes we visited expansion set. So in fact, this is only a linear number. You can just think about like how many nodes you need to save. So you need to only search the longest path. Okay, that's the Brownian vector, and then each one you save one, right? At most one, and then how many depths is d depths? So that is b to the power of d. Okay, at most b to bd, and big O of B multiplied by D. Okay. So this is the difference between this one and this one. This is how many nodes you need to visit. This is how many nodes you need to save in the expansion set. Okay, let's look at next question. We just mentioned about now, okay? So if, for example, if it's like this issue from Gulfport to Long Beach to New Orleans, so each step codes are not the same. They are not uniform. So how can we deal with this issue? Okay. So this is searching with varying step cost. So that means the costs are not the same. Okay. So that means we cannot use the previous method to do the search, because if you find a solution in lowest layer, okay, the depth is the smallest, but the cost maybe not, because you need to add all the past costs together, add all of them together. Even you find that this one, okay, is only layer 2, but maybe there's a deeper one, right? So the cost add them together is smaller. So if like that, so we cannot use that algorithm. So this is also called this is called the, I can say it's like a Travis-Mann problem, right? It's like that one, similar like that one. But is the difference is like for Travis-Mann problem, you need to visit each cities. But here is like you want to find the shortest path. Yeah, exactly like the shortest path distance, shortest distance path. Okay, search. Shortest distance path search. So in our algorithm course, we have this one as well. So that means you want to find the shortest path from the start to the goal, and then we already give you the weight for this one. So that means the path or the step, okay, step cost is not uniform. So BFS find the path with the fewest steps, but does not always find the cheapest path. Fewest path, because that fewest path will be the smallest cost. We assume that one is already uniform step cost, but here is not, so we cannot guarantee. Using BFS, you find the fewest steps, the shallowest one, that one will be the shortest distance. Maybe it's not the cheapest path. That's why we want to find something else. So how to find this one? In fact, for this one, since we already mentioned in the algorithm course, we have the shortest distance path algorithm. We know in that algorithm we use Dijkstra's algorithm. Dijkstra's algorithm is like we also call a new name called a uniform cost search. In fact, it's just another name for the Dijkstra algorithm. Let's look at how to do that one. So for here, we still adopt the same search strategy we mentioned before. We maintain the frontier node, and then we save the total cost of the path from the initial state to that node. So now we add this information to each node. So that means from the start node till current node, from here till here, what is the distance so far you have traveled so far? Each time we just update this one. If we visit this node again, we may compare with the previous recorded cost to see whether you find a shorter path to reach here. If it is, you need to replace it, okay? Same as the previous. Okay, so that means we need to save the total cost of the path from the initial state to that node. For each node in the frontier, okay, in the frontier, we need to save its total cost from the starting state, from the start state to this node, and then expand the frontier node with the lowest path cost. So here you can find out is different, okay? So here we expand the frontier with the lowest path cost. So that's the why we call disastrous algorithm, shortest path, shortest distance path search algorithm. So that means we want to grow our search by always finding the smallest path to expand. Okay, expand. So it's also called a greedy search algorithm, because each time you will find the smallest find a node with the smallest distance to grow, to visit. So for example, we want to go to okay, for example, we want to go to from New Orleans to Long Beach, and then we may visit several cities, and then we just find the closest city to the New Orleans every time till we reach Long Beach. So this is the idea. Okay, later we'll give you example. You will have deeper understanding of this one. So each time you grow a node with the smallest distance. Okay. So implementation will be a priority queue. So priority queue, if you have learned the algorithm or the structure, you know we can use a heap to do this one, correct? So for here, because its lowest path cost is smallest, so we need to use the min heap. Each time we maintain the smallest one on the top, on the root, okay, on the root. So we don't care about the lower levels, but we always have this min heap, means the root is less or equal to its left and right child. So you maintain a min heap every time. If you extract, that means remove one node from the root, and then you do the min heap file. Right? Min heap file, that means you need to reorganize the nodes to form another min heap. So min heap file, max heap file, right? And then you have min heap file. Min heap file, that means you want to fix the heap to make it has the min heap properties. Okay, just the root node is always less than or at most equal to its children. Okay, so we can use the priority queue. So this is not a big issue, because we know for min heap file, and then for this one, so this one is log n cat. So it's big of log n. It's very quick. It's very efficient. Okay, so that's why we use the heap sort algorithm. It is same as the merge sort, quick sort, which is big of n log n. Okay. Anyway, this is just some implementation thing. If you forgot, for example, you need to implement this algorithm in your AI agent, you can refer to that knowledge. That's not a big issue here. This one equivalent to BFS if the step costs are all equal, of course. If they're the same, and this one will just layer by layer, correct? Because lowest path must be this layer haven't explored. Some nodes in this layer haven't explored. That will be the lowest path, because each cost is the same, correct? Is 1. So you have to exhaust all the nodes in that layer and then continue with the next layer. Okay, let's look at this one equivalent to disaster algorithm in general. In fact, we also give a new name to it. It's just called disaster algorithm. Disaster algorithm based search. Okay, just same. Let's look at this example. For example, you have example you already showed before. So from the start to the goal, and then you want to find the smallest path, correct? So that path must be the smallest, and then for the steps we already have varying cost. Each step cost is different, so they're not uniform. So we do like that way. So we maintain a priority queue. Okay, priority queue for the nodes in the frontier. Each time we find the first one. The first one will be the mean, okay? Mean heap will be the minimum to expand. So it's like this. We expand. Maybe you have a frontier like that, and search one smallest, and then continue find the not smallest till you reach the goal. So this is the basic idea. Okay. Each time you search a smallest, you got a smallest, remove from the priority queue, mean priority queue, mean heap, and then expand. Okay. Then that means remove from the frontier, and then to check whether it's a goal or not. If it's not a goal, continue to find the next one to expand. Okay, so you add that one to the search tree. Let's look at the steps. So this one we draw in a more pleasant way, so that it will be easy for you to understand. We use a different color to represent the different frontier state. That means, for example, for here, initially is S, and then we can reach D, E, and P, and then coast is 3, 9, and 1. Okay? So that's why we save the coast, the path coast, as well to the nodes. Okay, that means that will be the shortest path from the start node to the current node. Okay, and then this is the frontier. We will search the smallest one. Which one is smallest? 3, 9, 3, 9, and 1. Okay, 3, 9, and 1. So that means you can find, of course, P for this one is the smallest. So that means you start from S and then with the P, and then you will continue with the next one. So this is 1, and this one is reach this one is too big. Reach this one is 9 is too big. Reach this one is better. Okay? And then you will explore D, and after that you can find here another frontier is S, D, and P and E. And then you can find which here is 4, and this one is 5. So this one seems better. Okay? So it's S, P, D, and B. After that, E is smaller. Okay? E is smaller. And then you can find A is smaller, and then R, and then continue. Okay? E. So this is the idea. So S, P, D, B, and then E, and then A, and then R, F, and then E. After that you got a G. You already got to reach this one. It's 10. Right? So this is 9. You already 9. That means you grow according to the distance. Of course, if you reach goal G, that will be because each time if you visit the nodes again, you will update the nodes cost. So if you reach the goal, you will always find the smallest distance to reach the goal. So this is the reason why you always maintain the reachable nodes with the shortest distances. Okay? Let me reach. So in fact here, when we find a goal, in fact you don't only find one path to the goal, your shortest path. You find all the shortest paths to all the nodes which have been visited, so you can recover. For example, if we want to reach E, you will get this one, correct? Because this one you will maintain this E, not maintain this one, because you haven't you visit this one, but you haven't used this one because this 9 is larger than 5. So this one will be not used. Okay, will not consider. We will still locate. We will still record this distance. With this distance, of course, you know what's the parent. Okay? So we always keep that information. So if we want to find the shortest path from E to E, you can also find is this one, the 5, and then parent is D, and then S. So you can reconstruct the path. Same as here, you can reconstruct. Okay, this is the uniform coast search algorithm. Okay, this is called coast contours. Yeah, coast contours. Maybe you can think about just like a watershed. So under this level, all of this one belonging to that one. Above is another watershed. Okay. So look at this demo to see its search path. We'll later compare this algorithm with some other algorithm based on similar demos. So you can find the problem is that seems still slow, okay? Yeah, but that's the because of this problem. There's an obstacle between, so the search will be slower. Okay, if there's no obstacle, you can find the answer quickly. In fact, digestion algorithm is also very popular algorithm in the graph algorithm set. Okay, properties, whether it's complete or not. Complete, that means if we have an optimal solution there, you can always guarantee you can find it. If there's no issue, if there's no issue with the step cost is greater than some positive constant epsilon. We do not want to have an infinite number of nodes to visit. If there's no this issue, the answer is yes. Okay, so you just need to confirm whether your problem has this issue or not. If it's no, you are sure, you have confidence in applying this algorithm. Optimal, if you find the solution, whether this solution will be the best. Yes, of course, because we mentioned about that property. We always save the nodes with the shortest path along the path of the search or in the search tree. And the next one is the time. Okay, time and space. We put them together. So the time is the number of nodes with the path cost less than the cost of optimal solution, C star. So please remember, so starting from here till the end of the course, we always use a star to represent the optimal solution. Okay, star to represent the optimal solution. Okay, that's why you can find we call this one the algorithm later called A star. A star means optimal. Okay, so this one C star means the cost of the optimal solution. For example, in that search tree, in that cannot say search tree, in that tree, you have a optimal solution. When we reach that node, you have the cost. Right? You have the cost of optimal solution. That means we found the path, we found the distance, we found the path to reach that optimal solution. And then for this cost is C star. Because we expanded the cost from smaller to bigger one, each one by one. All the smaller cost, all the nodes with smaller cost must be visited first before we grow into next cost. So you can find next higher cost. So that means all the nodes whose cost is less than this optimal cost will be visited. So that will be the answer. So what's that one? We use this notation to represent. It will be big O of the b to the power C star over epsilon. And then epsilon here is represent a lower bound on the cost of each action. Okay, so that means here we just each one at least we have this each action that means each from one node to another node. That means smallest cost for among the tree, among the search. So that one will be the epsilon. So it's C star over epsilon, and b to the power this one. This is just want to get the number of nodes. That means at least, at most, yeah, at least it will be smaller than this bound. This is upper bound. Is C star over this one, and this is the just like the layers. You can think about how many layers, because each coast, okay? Each coast maybe it's 1, maybe it's 2, but this one is just use the minimum, all of them, okay? So that means at most this number of layers, and each layer we said the Brownian factor is b, okay? So that means the cost will be, we mentioned before, okay? Then how many you will just based on the height. So the height will be this one. At most is h c star over epsilon. Okay. Okay, this can be greater than the, because this is like an upper bound. We may just set it higher, because even maybe we can find a better one, but we set it a tight upper bound or not tight. So this is not tight, just because we guarantee it will be at most cannot exceed this cost. That means at most it cannot exceed this scale of number of nodes, because this is not the exact number of nodes. It's like this change, rate of change. So this one can be greater than big of b to the power d. D we mentioned before is the depth of the optimal. That means the exact, the true, the real depth of the optimal solution. But d we cannot guarantee, we cannot get it. So that's why, right? So this one can be greater because we choose the minimum, and then divided by this one. So that means we may extend here, because this cost, each one is larger than the epsilon. So in fact, to reach here should be less than this value. This is the layers, this number of layers, C star over epsilon. So the search can explore long passes consisting of small steps before exploring shorter passes consisting of larger steps. So this idea is like we mentioned, have small steps and then larger steps. So that means we said maybe you will explore long passes, small steps before exploring shorter passes. So that means you have to maybe have a waste, okay? Because we expand based on we said it's like a coast contour. So you have finished all the smaller coast. So that means we said long passes, and then there's small steps. Small step means the coast is small, so increase a little bit. So for example, 1, 1, 1, 1. But maybe you can have a shorter path, but this coast is bigger. Is maybe 5. You can jump to here directly. So this path is shorter, but you have to exhaust all of the small coast steps to return to here, because we based on the contour, okay? The coastal contour. You cannot jump to the next contour, coastal contour, before you exhaust all the nodes in the lower contour coastal contour. So like the watershed, okay? You have to jump, to climb to the hill from the bottom to the top of the hill. If you are, for example, there's a port on some, there's a lake, maybe there's a lake on some on a hill, okay? There's a different watersheds, okay? And then the space is the same as this one. That means how many nodes we need to save, okay? During the search, okay? Okay, let's put them together. So that will be for BFS, DFS, and IDS and UCS. Okay, this is some typo. I see. Show it later. Okay. Anyway, it doesn't matter. So basically, this is just like we want to put all of the properties together, and then we know the B is the branching factor, maximum branching factor, D is the depth of the optimal solution, M is the maximum search path, and then C star is the cost of the optimal solution, Gn is the cost of path from start state to node n. Okay, so BFS we know it's complete, is optimal if all the steps are equal, that means uniform, then it's optimal. But if it's not, we cannot use this one. We need to use UCS. Time complexity is b to the power d, correct? And then space is the same. DFS is no, because we don't know whether we can reach the best, because we search deeper and deeper, correct? So optimal, this one, that means we may not be able to find a solution. This one, maybe if we find a solution, maybe it's not optimal because we just search along the depths. Okay. Time complexity is till you search the maximum depths. When you stop to search, that will be the upper bound. Okay. So you may visit it at most this number of nodes above the depth m. And then space, you just need to save along the path. That's why it's smaller than this one. And then the maybe smaller, we can say. The IDS is complete and optimal if all the steps are equal, means uniform. If it's not uniform, you cannot exhaust all the nodes in some layers, even use iterative deepening search. The depth iterative deepened DFS search algorithm. So it also cannot find the solution. And time complexity is the same as this BFS. You will exhaust all the nodes under each layer, right? So similar to this one. That's why I can find here. But better than this one, right? DFS, because this one is optimal and also complete. And the space is you can find space is similar like this one, right? But of course, because this we can reach the optimal solution D, right? When we reach that depth, we stop. That's why M will be replaced by D, just because you will reach the optimal solution to stop. This one you may reach some suboptimal solution M till M steps later. And the uniform cost search, so it's complete, optimal, and the time complexity is that how many nodes are smaller than the optimal cost. Okay? So that's the number of nodes with Gn. That means their cost from the start initial node to the current node less than this one. That means all the nodes which are smaller than the optimal cost will be visited. So it's big O of b to the power c star over epsilon. Okay, epsilon is a minimum cost for each action. Okay, this also conclude this uniform uninformed search. So that means for this chapter, we just talk about these 4 algorithms: BFS, DFS, and IDS, and UCS. So I can say maybe you have some knowledge about the BFS, DFS before, but maybe you don't know IDS, and you may also know UCS if you learn the algorithm by yourself. Maybe I believe in my algorithm course I may not be able to cover that one, but the idea or maybe introduced. So the digestion algorithm. Okay, so this is just digestion algorithm, like a greedy search, greedy in the graph search algorithm, but based on digestion algorithm. And IDS is just like extension of the DFS, but also borrow the idea from BFS. Okay. Okay, just try your best to implement this one. Also, you can refer to the code, but do not just copy paste the code. Okay, I want to see your efforts in your project. Okay, if I found the exact same code, so you have some problem. Okay. Okay, and then IDS and UCS, I think you may have some questions in your homework, maybe not in your project. Okay? We do some balance about these things. Okay, this is you can find this is an important part about chapter 3, and then we'll continue with the next one. Still in the chapter, I think it's still in chapter 3, but this one is called another section. It's called informed search. Okay, it's informed search algorithm. Okay. Okay, maybe I will upload this one first, and then I will continue with this one in the second video. So that will be better for you to learn.